Hi everyone, this is the second video. So few things about glycolysis one more time, just to summarize it. We said we grab a glucose and we end up breaking it down into two. In yesterday's video, I said pyruvate. I want to say now pyruvic acid. And I will show the difference in a few seconds. I also said we are investing 2 molecules of adenosine triphosphate, but we end up generating 4 molecules of adenosine triphosphate, and this is by substrate level phosphorylation. So here you will have 2 adenosine diphosphate, and here you'll have 4 adenosine diphosphate. We also said you have 2 molecules of NAD+, and they become 2 NADH and 2 hydrogen ions. And the sugar or the glucose essentially losing the 4 hydrogen. I wrote that summary yesterday. The only difference is I said now pyruvic acid. Now, reason I did it this way, because I want to distinguish between pyruvic acid and pyruvate. We know this much about glucose. We know glucose is C6H12O6, this one. Now you are taking 4 hydrogen from it, but then you split into 2 pyruvic acid. So I'm expecting the pyruvic acid to be then, molecular formula to be C3. Well, again, 12 hydrogen, but I'm taking 4 hydrogen. So I have 8 hydrogen divided by 2, 4. And I have 6 oxygens divided by 2. So that's what I'm expecting the molecular formula of pyruvic acid to be. Once again, I said it's a hexose right there, but don't forget the fact that you are taking 4 hydrogen away to reduce the NAD+. And you subtract the 4 from the 12 hydrogen, you have 8 hydrogens left, but you then split into 2 molecules, so everyone's going to receive 4. And you do the same with the oxygen. Oxygen 6 divided by 2. And that is that, like, see, we were able to predict at least the molecular formula for pyruvic acid right there. So pyruvic acid, now if I want to show you the structure, it's 1, 2, 3, at least it's a C3. It is what did I want to say? It's a carboxylic acid, meaning it has a COOH, carboxylic acid. It's an organic acid. COCH3. This is it. So add again 1 carbon, 2, 3. That's your C3. Hydrogens, you have 1, and you have 3 here. That's a 4. Oxygen, you have 1, 2, 3. So this right there is pyruvic acid. You know pyruvate? What pyruvate is? Pyruvate is this then. It's basically the ionized form of pyruvic acid. Here, the ionized form of pyruvic acid. because an organic acid will ionize, will release a hydrogen ion, so I can release it here in an aqueous environment. And of course, it is an aqueous environment. All these reactions are taken inside the body, right? This is inside the cell in the cytoplasm. So when you read anywhere, just know the difference between the two. It is pyruvic acid, but it doesn't stick around for long. Pyruvic acid is short-lived. It's gonna become pyruvate because it will ionize, because it is an acid, and that's what acids do in aqueous environments. So that's one thing I needed to bring to your attention. And notice it's adding up. I said when I came up with that summary in yesterday's video, like you should right away predict pyruvic acid to at least have the molecular formula C3H4O3. Like that was a prediction, but it's a scientific prediction based on the summary you are looking at right now. All right, so that's still messing with glycolysis from yesterday. Let me do something else also about glycolysis. In yesterday's video as well, I mentioned 4 phases here, glycolysis. And I said you have phase 1, and we called it sugars activation or sugars phosphorylation. And I did tell you which sugars, the 2 sugars that are being activated by being phosphorylated. I said you might come across this term as well, the energy investment phase. Why is that? We said because you are investing energy, and in this phase we invested 2 adenosine triphosphate. And I also said that was a 3 reaction phase, and 2 adenosine triphosphate invested. All right, it's just quick reviews, but I'm getting somewhere with this. Phase 2, I called it the sugar, not sugars, sugar cleavage. And you should know which sugar. The sugar that is being cleaved, that was fructose 1,6-bis phosphate. And I said this is A2 reaction phase. And then phase 3. And I called it yesterday the redox phase of glycolysis, and it is A1 reaction phase. At least that's how we did it. I want to say a bit more about this phase right now, and actually a bit more about the last phase, the redox phase of glycolysis. And I said it's only 1 reaction. Of course, it's in the first video, but let's do it again and look at something that I did not bring up last time. So what do I have? I have 2 molecules right now of glyceraldehyde 3-phosphate. I said I end up with 2 molecules of 1,3,bis phosphoglycerate. I said you have 2 inorganic phosphate groups from the cytoplasm going in. And then I wrote this coenzyme business. I said 2NAD plus into 2NADH and the 2 hydrogen ions. And I did this. So none of this is new. Reason for the 2 everywhere, because remember again, you do have 2 glyceraldehyde 3-phosphate. So the reaction is being repeated twice. All right, what I want to say today is we did define also last time why it's a redox reaction. I said the oxidation because the glyceraldehyde 3-phosphate is being oxidized. The red because NAD plus is gaining the hydrogen and becoming reduced. Like it has been taken care of already. But now I'm gonna bring up this term, reducing agent. It's in this reaction, glyceraldehyde 3-phosphate. And let me write the other term and then walk you through it. Oxidizing agent. It is NAD plus. You do agree with me that glyceraldehyde 3-phosphate is losing hydrogen. And those hydrogen are used to do what? To reduce the NAD plus, hence reducing agent. It is the one, glyceraldehyde 3-phosphate is the reason why NAD plus is becoming reduced. So I am the reducing agent. And now, NAD plus is taking the hydrogen away from glyceraldehyde 3-phosphate. So it is the reason glyceraldehyde 3-phosphate is becoming oxidized, hence oxidizing agent. So do not confuse what is being oxidized by oxidizing agent, because they are actually the opposite. So one more time, if you look at this, let me clean it up again. Here. All right, if I look, let's do that. Glyceraldehyde 3-phosphate is losing hydrogen. Again, glyceraldehyde 3-phosphate losing hydrogen. So it is becoming oxidized, but it is reducing the NAD plus, because the hydrogen you are taking away, or glyceraldehyde 3-phosphate is losing those hydrogen, and those hydrogen are being used to reduce NAD plus. So that's why it is a reducing agent. But it is getting oxidized. So glyceraldehyde 3-phosphate, one more time, is being oxidized. And the same thing here, but the other way around. Now, NAD plus is gaining hydrogen, so it's being reduced, because it's gaining the hydrogen, but it is oxidizing glyceraldehyde 3-phosphate because it's taking the hydrogen from glyceraldehyde 3-phosphate, hence the term oxidizing agent. So I needed to bring that to your attention, because it is a big deal, like we need to understand. I also told you to look up the name of the enzyme. I mean, it's everywhere. You will find it everywhere. Some will name it slightly differently than other sites. But think about it this way. The name that is very actually common isn't glyceraldehyde 3-phosphate a triose? So they call it triose phosphate. I'm not done. I'm just sharing one name, triose phosphate. What triose phosphate? They are referring to this. That's a triose phosphate, because glyceraldehyde 3-phosphate is a triose. It's a glyceraldehyde with a phosphate group. What is the enzyme doing to it? Dehydrogenating it, because it's taking hydrogen away from it. Hence, the full name, triose phosphate dehydrogenase. The names often are descriptive. So this is the enzyme that is dehydrogenating, glyceraldehyde 3-phosphate, which is a phosphorylated triose. A phosphorylated triose. There are other names. Some will actually call it glyceraldehyde 3-phosphate dehydrogenase. That's fine. But I said you can relate to where the name is coming from. All right. Again, none of this is really new. It's just, I said, just more emphasis of what we did yesterday. Yes, maybe we just introduced the reducing agent and oxidizing agent, but they are making perfect sense. I'm guessing, I hope. And the same with the enzyme I just inserted. All right, I'm gonna quiz you soon. But before, remember the phases again. Phase 3. Now phase 4. Phase 4. And yesterday, or in yesterday's video, I called it the substrate level phosphorylation. Before I continue, I said substrate level is this. The concept in general is you have an enzyme. I said E for enzyme. You have the substrate, one more time, which is the target of that enzyme. And you have adenosine diphosphate. So one more time, the substrate is becoming dephosphorylated, losing a phosphate to diphosphate, which is becoming triphosphate. And that's what we care about. And the substrate is becoming something else. It's losing a phosphate. This is the idea of substrate level. So once again, the term phosphorylation, that's because adenosine diphosphate is being phosphorylated. So right here, adenosine diphosphate is being phosphorylated, like getting a phosphate from somewhere. Where is that somewhere? The substrate. So substrate is being dephosphorylated, and adenosine diphosphate is being phosphorylated. One is losing the phosphate, one is gaining the phosphate, and the enzyme is facilitating the transfer of the phosphate between its substrate and adenosine diphosphate. Again, the enzyme itself is facilitating the transfer of the phosphate group from its substrate to adenosine diphosphate. If I want to use, let's say, this triangle as a substrate, and here it has a phosphate group, for example, and this is the enzyme, and this is adenosine diphosphate. So that phosphate will get transferred here. As a result, I have adenosine triphosphate, and the triangle will lose that phosphate. But there is more that will happen to it. So let's say like 3 lines for a triangle. Let's say this line, that line, this line. I'm trying to say there are other changes other than taking the phosphate. But all what we did really, or the main thing I care about right now, is I took that phosphate away from the substrate and I transferred that to adenosine diphosphate. So when I wrote, let's say, the very last reaction of, when I wrote for this phase 4, I said it's a 4 reaction, here, A4 reaction pathway or phase. Notice that only 2 of the reactions are substrate level. Like when I write, for example, when I write phosphoenol pyruvate 2-pyruvate, and I said pyruvate here, pyruvate kinase, and here I did this adenosine diphosphate, adenosine triphosphate. Yes, that qualifies as substrate level. It fits exactly the description we just did. So phosphoenol pyruvate is losing a phosphate to adenosine diphosphate, which is becoming phosphorylated into adenosine triphosphate. But when I look at this reaction, it's a 2-phosphoglycerate into phosphoenol pyruvate. Well, that's not a substrate level, but it leads to a substrate level phosphorylation reaction. So what I'm saying here in English, when I say a 4 reaction pathway, not every one of the 4 reaction is a substrate level. The phase itself is a substrate level because energy is being made. So look at the 4 reactions again. I still believe I have them from yesterday here because it's the same notes. Let's see. Yeah, right there. Remember all that from yesterday. So substrate level, exactly what I did. So right here, let's see. Like this reaction, for example, that's not a substrate level, but this one is right there. And the same, this reaction here is not a substrate level, but this one is. All right. A bit more about the substrate level phosphorylation business because it's going to come up. There are 2 ways to make money here. 2 mechanisms to make adenosine triphosphate. One is what we just did, substrate level phosphorylation. Substrate level phosphorylation. The other one is oxidative phosphorylation. Here, oxidative phosphorylation. Now, what's this one? I don't know yet, but keep it in mind because it's going to come up. So, but we know already one of them. So I said there are 2 mechanisms, 2 pathways by which you can make adenosine triphosphate. One of them is substrate level phosphorylation, which we have a very nice idea what that is. And I said oxidative phosphorylation, which we are not exactly sure what that is yet. So we will come back to that as well. I want to give you a question here. I'm not going to answer it in this video, but I will give it to you and I will see if you can do it, and I will eventually take care of it. Let's say here, I'm quizzing you, quiz. Let's say on the exam or the quiz, whatever, you have this question. So you have this reaction. Let's see, you have A. I'm going to make it up right now. A, B, let's see, you end up with, let's say C6, H6, O6, whatever that is, we don't care, plus C, what else do you want to do? Plus N, A, D plus. And let's say H2O going in, CO2 coming out. And the question is, let's make sure here, A, B, C. What do I want to do to this? Wow, I can't think of what I want to ask, believe it or not. Let's see. All right, I don't want to take it forever, take forever. Let's just add. I'll tell you what, sorry about this. I need to think of, we didn't do the transition yet, so I'm gonna save it. Give me a second, sorry. We'll come back, promise. Every time I think of something to ask, you're still missing a piece of information, I guess. All right, it's okay, sorry about that. Next phase, after glycolysis, and I remind you again, that's what I have from first video here. That's my summary or my inventory right there. I said, as a result of glycolysis, you have 2 pyruvate, 2 molecules of H2O, 2 NADH, and 2 adenosine triphosphate cache. You did release 4, yes, but you don't have the 4 because you had to pay the 2 that you borrowed, the 2 that have been invested. All right. Everything from this point on, oxygen needed. And that will include 2 transition, that's what I called it at least, transition phase. And then the Krebs cycle here, Krebs cycle for the electron transport system, All right, let's look at the transition phase. Remember, oxygen is needed and mitochondria will be needed as well, as we said also in the first video. All right, the transition phase. Transition phase. What do I have right now? I have 2 pyruvate from glycolysis. Okay, so the transition phase, the 2 pyruvate from glycolysis will get transported into the mitochondrion and they will become 2 molecules of acetyl coenzyme A. So this again here, from the cytoplasm. To be exact, from glycolysis. We said before that this reaction is taking place in the mitochondrial matrix. All right. At the same time, you need 2 molecules of coenzyme A. They are going in, coming from food. This reaction, or in this reaction, 2 CO2 are being released. Also, 2 more NAD+ are becoming 2 NADH and 2 hydrogen ions. So same, that means 4 more hydrogen are being taken away from the pyruvate in this specific case. This is a summary of the transition reaction. We need to spend some time breaking it down. When I looked at glycolysis, I said I have a net gain of 2 NADH. I guess I have 2 more, so now I have 4 of them. And I also said these are checks to be cashed, so it is money. This transition phase, the name transition because it is transitioning between glycolysis and the Krebs cycle. Because remember, number 1 was glycolysis. So in glycolysis, we had 10 reactions, and the Krebs cycle is busy as well, where it's a major component of metabolism. So transition, the term transition, because it is really transitioning or linking the events that are taking place in the cytoplasm to the major event or events that are taking place in the mitochondria, which is really the Krebs cycle. That's where transition is coming from. But now we want to, we know more, or we know more about that transition phase. So we want to come up with a more, I guess, descriptive term for it, which is, look, pyruvate. What is going on with the pyruvate? The pyruvate is clearly getting oxidized, losing hydrogen. But it is, which means it's getting dehydrogenated. But it is also getting decarboxylated because you're taking carbon away from it. It's being decarboxylated. So this transition phase, so the reaction above the transition phase is an oxidative decarboxylation reaction. I will repeat, oxidative because pyruvate is losing hydrogen, so it's being oxidized. Decarboxylation, decarb, because it's also losing carbon in the form of CO2. So now we know that the transition phase is an oxidative decarboxylation phase. It is an oxidative decarboxylation phase. So in the transition phase, again, pyruvate is getting both oxidized, which means dehydrogenated, as well as decarboxylated. All right. I'll sit in here. Okay, I think we are okay for now about this phase. Krebs cycle. What do we know? We know it's in the mitochondrial matrix, the same as this, right here, mitochondrial matrix. So the same. Mitochondrial matrix. I will also break it down into several phases. So what we have so far, again, right there, look, you have 2 molecules of acetyl-CoA. 2, not 1. Which means I'm going to go ahead and fire that Krebs cycle twice, because I don't have 1 acetyl-CoA, I have 2 of them. So what I will do is actually trace 1 acetyl-CoA. So think of it that way again. Look, if you look at 1 pyruvate, I have 2 pyruvate, but if you look at 1 pyruvate, so here, 1, pyruvate, but I'm gonna say, don't forget that we have indeed 2 pyruvate. So 1 pyruvate will give you 1 acetyl-CoA. That's your transition reaction so far, without showing the toys in the reaction. But now I'm going to trace that acetyl-CoA. So acetyl-CoA is going into, like it's going to fire that Krebs cycle. All right. Krebs cycle is also busy, so I'm going to pick and choose what I want to emphasize. The acetyl-CoA is going to merge with oxaloacetate. Oxaloacetate. And the two will merge, will meet, and will end up forming citric acid. Let me just say a few things. I said oxaloacetate. I could say oxaloacetic acid. I said citric acid. I could say acetate. Remember the difference between pyruvic acid and pyruvate. All these guys are organic acid, and they will eventually ionize. All right, so citric acid. How does you have to be careful, you have to pay attention, you have to trace all the hydrogens, all the oxygens, or everything, you have to trace it for this to make sense. So citric acid, to the side, to the most right, let me show you how it looks like. COOH. I'm showing you what citric acid. CH2. C. COOH. And OH here. CH2. Excuse me. COOH. That you are staring at citric acid. Again, citric acid. What I need you to pay attention to, then I expect you to be able to tell me that oxaloacetate here is a C4 compound. Look, without me telling you why, you have to pay attention to this stuff. How come? Because citric acid has 6 C's in it. You count 6 C's in citric acid. Okay. And I expected acetyl-CoA to have 2 of them, 2 C's in it. Why? So C2. I will show you why in a sec, but look, C2 merging with the C4, that's why you have the C6. So now how did I know that acetyl-CoA is a C2? Okay, to the side here. I'm going to do it here and erase it. Here, right there, inside this box, and erase it. We said pyruvate is becoming acetyl-CoA. See that CoA? That was going in here, CoA, coenzyme A. So I'm not talking about this. I'm talking about the acetyl group. Isn't pyruvate a C3? But did you not lose a C in the CO2? So that's a C2 then. So one more time, pyruvate is a C3, but the C3 did lose a C in the CO2. Then that's a C2. That's how I figured it out. So C2 must be combining with the C4 if I really ended up with a C6. And I did. All right, before I still continue, I said, they might not really, like when you read anywhere, no one is going to kind of bring that to your attention, but it's essential to notice, to understand. Also, why is it called the Krebs cycle? Look, let's actually look at those names. Krebs, that's just after the guy that discovered that cycle. His name is Hans Krebs. But the same cycle is also called, look, the citric acid cycle. Yeah, why? Because the first intermediate form in the cycle is citric acid. The first intermediate form in the cycle is citric acid, hence the name, the citric acid cycle. So, you know, I need the space for the cycle, but let me write this down right there. So Krebs cycle, here also known as citric, acid cycle. And I said, why so? Because the first intermediate formed in the cycle is citric acid. Okay, what else? And it's also called the TCA cycle. Why do you think it's called the TCA cycle? Because the first intermediate formed in the cycle, let me do it this way, is citric acid, right? Which is a tricarboxylic acid, which is a tricarboxylic acid. It has 3 carboxyl group. So citric acid is a tricarboxylic acid. It has 3 carboxyl group. So going down again, this means the tricarboxylic acid, which is, the tricarboxylic acid, and we are referring, remember, to citric acid, which is the first intermediate form in the cycle. The tricarboxylic acid, which is citric acid, which is the first intermediate formed. All right. Going back to the cycle. Citric acid will eventually become citrate. So whether I use citric acid, citrate, isocitrate, we are not going to swear it. So after citric acid, you will end up with isocitric acid. I'm just going to say isocitrate. Isocitrate. Isocitrate will become alpha ketoglutarate, well, which is alpha ketoglutaric acid, but then ionizes into alpha ketoglutarate. So here, alpha ketoglutarate. I'm going to write one more reaction, then go back to the isocitrate. The alpha ketoglutarate is becoming succinyl-CoA. Succinyl-CoA. Let's stop here before I finish the cycle. You know what? Let's actually finish the cycle and then plug in the missing components from succinyl-CoA into succinate. From succinate into fumarate. From fumarate into malate. And from malate into oxaloacetate. Of course, we're missing quite a bit, but that's what I care about today. All right, so let's add a few things. One more time, this reaction or the Krebs cycle is being fired twice because I said do not forget that we have 2 pyruvate molecules, not just one. I said the pyruvate is losing a CO2. That's why it's a C2, losing a C in the CO2. And that's how I predicted that oxaloacetate is a C4, because C4 and C2, that's your C6, which is the which is the citric acid. All right. From alpha ketoglutarate, from the isocitrate to the alpha ketoglutarate, this will happen. NAD plus is becoming NADH and hydrogen ion. Remember, I need two hydrogens. And not only that, and CO2 is also released from isocitrate. The same exact thing is happening here. So I'm going to do it on this side. NAD plus NADH and hydrogen ion, the two hydrogen and CO2. Okay, this phase, what phase? From the isocitrate, look, from the isocitrate to the succinyl-CoA. Why this is any different than what we did in the transition? Look what we call the transition. I called it an oxidative decarboxylation reaction because we oxidized pyruvate and we decarboxylated pyruvate. Did we not do the same thing here? But it's not pyruvate. So going down, what did we do to isocitrate? We oxidized isocitrate and we decarboxylated isocitrate. Isn't that what we did to alpha ketoglutarate? We oxidized alpha ketoglutarate, we decarboxylated alpha ketoglutarate. So this phase of the Krebs cycle is the oxidative decarboxylation phase. The oxidative decarboxylation phase. So here, phases of the Krebs cycle. One, the oxidative decarboxylation phase. And I'm showing you what it is. I said from the isocitrate to the succinyl-CoA. Here, from isocitrate to succinyl-CoA, sorry. To succinyl-CoA. All right, the second phase. Let's go back. Let me erase this. What I'm going to do here, from succinyl-CoA to succinate, you have guanosine diphosphate. Guanosine diphosphate, gaining an inorganic phosphate and becoming guanosine triphosphate. Then the guanosine triphosphate is losing that phosphate and reverting back to guanosine diphosphate, but it's losing that phosphate, that's how you write it down, to adenosine diphosphate, which is becoming adenosine triphosphate. So I will repeat. You have an inorganic phosphate in the mitochondrial matrix that will be seized by guanosine diphosphate, which is becoming guanosine triphosphate. But it does lose it. It's going to lose it right away. Lose it to whom? Going to lose it to, no one does what I'm doing here with this, but just so you know. Like it's implied, you don't need to do what I just did. The guanosine triphosphate loses that phosphate to diphosphate. Thus, guanosine triphosphate reverse back to guanosine diphosphate, and adenosine diphosphate received that phosphate and now is adenosine triphosphate. You know what that phase is? That's substrate level phosphorylation. So that's the second phase, substrate level phosphorylation phase. I understand it's quite a bit. Look how busy everything is, like different language altogether, but I have to make sure I keep watching those videos and reading the book, reading everywhere to click. All right, one more phase. From succinate to fumarate. Succinate to fumarate. You have another coenzyme that I did not mention before. This is the very first sign. It's FAD, and I will tell you what it is, but no plus sign, unlike NAD plus. So no plus sign. FAD is becoming FADH2, in which the succinate loses 2 hydrogen to the FAD. And the FAD will grab the 2 full hydrogens and will become FADH2. So let me go down a bit here. I will write the third phase in a second, but FAD, and I'm going to see here, no plus sign, unlike here, unlike NAD plus. What does it stand for? Flavin. The AD the same. Remember the other one, nicotinamide adenine dinucleotide? So the same, adenine dinucleotide. So what happens is FAD grabs 2 full hydrogen and becomes FADH2. So it is a coenzyme electrons carrier. But this one is unique to the Krebs cycle. Unique to the Krebs cycle. We did not come across FAD anywhere else. All right, going back to that Krebs cycle. So the FAD is becoming FADH2. Fumarate into malate, but this one requires 1 molecule of water, like going in, needed. And then the last reaction, malate into oxaloacetate. So you have NAD plus, NADH, and a hydrogen ion, 2 more hydrogen. So what did we do? Look at the difference, because I want to come up with a name for the third phase, which is from the succinate all the way to the oxaloacetate. What did we do to succinate? We just oxidized. We did not decarboxylate. What did we do to malate? Same. We just oxidized, but we did not decarboxylate. I did not do this. I did not do this. So the third phase is oxidative phase, not oxidative decarboxylation, just oxidative phase, which is from where to where? Remember again, look, it is from the succinate, from here, to oxaloacetate. Succinate to oxaloacetate. Gosh, okay, tons of inventory that needs to be done and analysis. How do you know, by the way, if I actually did this, look, I'm gonna do something that is not right, and I will fix it, of course. If I go to this reaction from malate to oxaloacetate, and do this, I will do it and I will erase it, of course. What I just did right there. You actually should know I'm lying. You should know I'm making this up and it's impossible for this to happen. This is what I mean by comprehension, by understanding. How come? Like, again, I wish we were in class so we can go back and forth about this forever, for like 15 minutes. I can't do this now because I'm speaking to myself, of course. So why this is, like, if I said, if I did it, if you were paying attention, you know, to everything, you would say, oh, stop, what the heck are you doing? I mean, you can't trick me. That's impossible. How come? So I'm going to get rid of it. There is no such thing as CO2 being released here. This is garbage. But how do you know? Because you know this. You know the main reaction of cell respiration. C6, H12O6 plus 6O2 into 6 CO2, 6 H2O. I'm going to see if say E for energy. I'm expecting 6 CO2. I don't have more than 6 because once I take all the hydrogens, I will have only 6 CO2 left. What I mean by that, 6 carbons, because right there, I took all the hydrogens. How many C's do you have? 6. If you take the hydrogen away. Okay, did I not release 6? I did already. How? Let's do the inventory. I released 2 in the transition right there. 2 of them in the transition. I released 1 and 1. But that's per pyruvate. But I have 2 pyruvate. So this cycle is being fired twice. So that's my 6. You see again? So every Krebs cycle is releasing 1, releasing 1, 2 of them. Every firing of the Krebs cycle. I'm going to fire that cycle twice. That's 4. And the 2 you release in the transition, that's your 6. I'm done oxidizing the sugar. Done. Where are you done oxidizing? What is the point by which the oxidation is concluded? Right there. Because I already oxidized the sugar. So that's how I was able to tell there is no more CO2 being released, because I was expecting 6 and I already have them. One more time quickly. I said 2 of them are coming from the transition. And the Krebs cycle is being fired twice, CO2 times 2, 4, and the 2 in the transition, that's my 6. So when I do something like this, and I will do it and erase it again, oops. Here, when I do this, gosh, let's go back. If I go ahead and add CO2, right away, you should know that this is just garbage. That's not the case. All right. Let's do a big, gigantic inventory. Which is pair 1 molecule of glucose. All right, glycolysis. Let's make a table. Glycolysis. Transition. Krebs electron transport system. Let's see how much we know and how much we don't know. What do I want to do? No, I need to lower this a bit. All right, let's say ATP. And this is when I said 1 molecule per glucose, and this is net. All right, ATP, let's say NADH, FADH2, CO2, H2O. All right, in glycolysis, use in glycolysis, the net was 2 adenosine triphosphate. We invested 2, we released 4, so net is 2. NADH, go back to glycolysis, 2 of them. FEDH2, I did not bring that up in glycolysis. CO2, I don't think so. H2O, we ended up releasing 2 of them, and I'm going to take you to glycolysis from yesterday's video even. All right, coming up right here, where are we? Here. Okay. In transition, I don't go back to transition. We did not release any ATP, NADH2 of them. FEDH2 still 0, CO2 2, H2 on recall. Krebs cycle. Well, remember again, the Krebs cycle is being fired twice. I said net pair 1 glucose. So you have 2 adenosine triphosphate here, right there. But that cycle is being fired twice. NADH6, let me show you the 6. NADH, NADH, NADH times 2 firings. That's Y6. FEDH2, 2, because in 1 firing of that cycle, you end up with 1. This one here. All right. CO2, 4, we emphasize that. And H2O minus 2, because go back to the Krebs cycle right there. I need 1 H2O for every firing of the Krebs cycle. That cycle is being fired twice. And by the way, the CO2 one more time, CO2, CO2, but I have 2 firings. That's why I wrote down 4. So guys, electron transport system, I don't know much about it, but I really know almost everything about it. Why? Because I know what the final outcome is. Meaning what? Like if I go ahead and do this summary at the very end, how many adenosine triphosphate did I say I should have at the very end when I'm done with my mess? I said 36 or 38. Well, I only have 4. So I guess 32 or 34. It has to be because they had to add up to what I was promised. All right, the final reaction doesn't have any NADH and doesn't have any FADH2. So I guess minus 10 minus 2. CO2, I should have 6. Then it's 0 because I already have 6. H2O, I should have 6 at the very end. Well, I don't have any. I did make 2, I used them, so I guess I need 6. So look, I know all the numbers. So I'm trying to take you to that electron transport system. Okay, so that being said, from that electron transport system that I don't know the details of it yet, but I know this much about it. I'm cheating basically. I know I'm gonna end up, look, I'm gonna use those numbers to come up with a summary for it. So one more time, guys, I just plugged in all the numbers and I said, wait, when I'm done with my reaction, I should have this many ATP. I only have so far 4 of them. So I guess the 32, the 34 missing must be coming from electron transport. I know the final reaction doesn't have any DH. I have 10 of them, 2, 2, and 6, then I guess they have to disappear in the electron transport. The same with the FEDH2. CO2, I should have 6. I already generated the 6. I shouldn't make any. H2, I should have 6. I don't have any because the 2 that I made in glycolysis have been consumed in the Krebs, so I need 6 in the electron transport. That being said, look, why can't I come up with a summary for the electron transport? And that's how I'm going to do it. How many H2O you need? Right there. Here, I need 6 of them. So see that number is taken care of here. 6 H2O. I'm sorry, this number I meant. I need 32, 34 ATP. Fine, here. 32, 32 or 34 adenosine triphosphate coming from 32 or 34 adenosine diphosphate. All right, I took care of that too. Now let's take care of that negative 10, negative 2. So clearly, I'm doing something more or less like this. The 10 NADH I generated, they are being oxidized into 10 NAD plus, and the 2 FADH2 I generated are being oxidized into 2 FAD. So those 10 and those 2 are those 10 and those 2 that we generated in glycolysis transition and Krebs. So NADH is becoming oxidized into NAD plus, and FADH2 is becoming oxidized into FAD. They are losing the hydrogen. Who do you think, or whom do you think they are losing the hydrogen to? Here, hydrogen, and the same thing, hydrogen. What gains hydrogen to become H2O? Isn't that oxygen? I don't need to balance the equation, but that's how, it has to add up. So oxygen is doing what? Oxygen is the oxidizing agent. Oxygen, I said, is the oxidizing agent. Look how I said it. Why? Because it is oxidizing NADH and oxidizing FADH2. So oxygen is gaining hydrogen, becoming reduced. Gaining hydrogen and becoming reduced. So oxygen is the final destination for the electrons. I will repeat, oxygen is the final destination for those electrons. But we know that. But now we're like, why did I say we knew that? Because when we started the reaction again, C6H12O6 plus 6O2, isn't that what I said we do? You take the hydrogen away, and that's why this becomes the CO2, the 6CO2, and the O2 gains the hydrogen and becomes the water. Forget the energy for now. So the sugar loses hydrogen and becomes CO2. We said that's oxidation. The O2 gains the hydrogen, becomes reduced into water. Reduction. But now I know more about it. I know that, like, I see the oxygen at the very end did receive those hydrogens and became reduced into water. So if you look at that electron transport system, which is in the Christie, as we also said before, it is nothing but an ATM machine. Why did I say that? Because I'm taking the checks, the 10 NADH and the FADH2. These are checks, and somehow I'm walking out or walking away with cash money, ATB, electron transport system. To add the numbers, I'm not going to finish electron transport system in this video, but to make the numbers add up, think of it that way. Every time you are taking one molecule of FADH2 to the electron transport system, and you can't go there without oxygen. Remember, oxygen, that's something that requires oxygen. You will cache it into, this is where the book and I will be a bit different. The book is saying 1.5. I want to round it up and make it 2 adenosine triphosphate. And this is a number you are responsible for on the exam or any quiz, not the 1.5. So we'll see how, but again, for our sake, every time you are taking an FADH2 to cache it, we will stick with the 2 adenosine triphosphate as our key. Now, every time you are taking one NADH DH. Here you have to distinguish the cytoplasmic from the mitochondrial, because FADH2 was just mitochondrial from the Krebs cycle. There is nowhere else we made it. NADH is coming from the cytoplasm, which is cytoplasmic, but also coming from the transition and Krebs, and these are mitochondrial. Like, look at the table right there. So these here are mitochondrial. That's transition and Krebs. This is cytoplasmic. But the FADH2, I said it just was one source, which is in the Krebs cycle, which is mitochondrial. All right, so going back, every NADH, if mitochondrial, then 3-adenosine triphosphate, pair 1. The book will say 2.5. If cytoplasmic, then 2 or 3 ATP. Which cells will give me 3? Only cardiocytes and hepatocytes, liver cells. 2, all other cells will give you 2. Okay, that being said, let's go back. I want to basically justify to you that when I took 10 NADH and 2 FADH2 to the electron transport system with oxygen, of course, I said I end up with 32 or 34 adenosine triphosphate. I want to use the key to show you they will add up to what I just said. I'm talking about this, guys, here. Right there. I took 10 NADH, I took 2 FADH2 to the electron transport system, 10 NADH, 2 FADH2, and I ended up with the 32 or 34 ATP. All right, so let's do this. Use a different color. Use black. I have 2 FADH2. Based on the key, the 2 FADH2 going to the electron transport system will give me 2 each, so 4 adenosine triphosphate. I have 10 NADH, 10 NADH, but those 10 are 8 and 2. What do I mean by that? 8 of them are mitochondrial and 2 are cytoplasmic. Go back to the table. Here, 8 are mitochondrial. And I said the mitochondrial will be cached into 3 each. So electron transport system with oxygen. So 8 times 3, 24 ATP. The 2 cytoplasmic will be cached into 2 each or 3 each, 4 or 6 ATP, depending what cell it is, as I said before. Add them up. What do you have? You have 4 and 24, that's 28. 28 and 4, 32 or 34. That's it, they add up. We still did not do the electron transport system, but I'm showing you how the numbers add up. Now, earlier I said there are 2 ways to make money. Remember here, somewhere, where did I write it down? At the beginning of this video. Here, the substrate level and oxidative phosphorylation. Now, this is oxidative phosphorylation. What is going down? going to the summary here. You are staring at oxidative phosphorylation. Think of it. Of course, I said I will not go over that in depth in this video. But the term oxidative phosphorylation, look, you need to oxidize the coenzymes to phosphorylate adenosine diphosphate. So electron transport system is oxidative phosphorylation. Electron transport system is the same as oxidative phosphorylation. Please, by the way, everything I'm saying right now is actually, I do have my typed notes in the Google Drive. They are my own notes. I did not steal them from anywhere. They are really my own notes. Like, you know, you can tell when you read them that this is my language. I have a very precise description of everything I have been talking about in the Google Drive. I know it's a lot to take in, but that's, you know, it has to be done. So refer to that, please, as well, of course. All right, so the electron transport system, I said, is the same as oxidative phosphorylation. And one more time, what we do is we must oxidize the coenzymes. And which coenzymes? NADH plus FADH2 in order to phosphorylate adenosine diphosphate. Hence the name, oxidative phosphorylation. Hence the name, oxidative phosphorylation. And still one more time, I said in that reaction, for us to be able to generate without numbers to phosphorylate adenosine diphosphate, you need to do this. You need to grab NADH and FADH2. So they are being oxidized. That's, I said, where the name is coming from. You must oxidize the NADH. You must oxidize the FADH2. Look, they are losing their hydrogen in order to be able to phosphorylate adenosine diphosphate. That's oxidative phosphorylation. Very different than substrate level phosphorylation. What else I want to say here? Okay, let me end this recording with a question now. If I say you have one molecule of glyceraldehyde 3-phosphate, one molecule of glyceraldehyde 3-phosphate, and you have a leukocyte, and I want to know the net adenosine triphosphate yield, A, with oxygen, B, without oxygen. And to answer that question, you need to know all your reactions inside out. We have to be quick. I said, I did warn everyone that this unit is very heavy. So you're starting here. So that's what you need to do. Glyceraldehyde 3-phosphate. What's next? Next is 1,3-bis phosphoglycerate. What do we do here? you have one molecule of NADH generated from the NAD plus, like this. See, I need to know all this to answer the question. So is this something I need to come back to? This one? Yes, that's, remember, that will be cached. So that's something. So I said start right there. Okay, 1 3-bis phosphoglycerate into 3 phosphoglycerate. But that reaction is a substrate level phosphorylation reaction. Like, will give you cash money right there. From adenosine diphosphate, because this guy is losing a phosphate to the diphosphate. So that's another thing that we need to come back to. 3 phosphoglycerate into 2 phosphoglycerate. 2 phosphoglycerate into phosphoenol pyruvate. Phosphoenol pyruvate, sorry, phosphoenol pyruvate. Let me clean it up. All right, into pyruvate. But that is another substrate level phosphorylation reaction. So this is, I can answer this question already. Look, when I said without oxygen, well, I can't do anything after this point without oxygen. I'm done. I can't proceed. So the answer is just 2 adenosine triphosphate. What 2? This one and this one. So that's the answer for this one, at least 2. What else do you want me to do? Nothing. Without oxygen. 1 and 1. That's substrate level phosphorylation. Substrate level phosphorylation. Can I cache NADH? No, not without oxygen. Remember, I said no oxygen, so I can't. Now, A, with oxygen, I'm going to continue then into acetyl-CoA. But that also gives me an NADH. I care about this, of course, from NAD plus. Yes, I release a CO2. All right. Acetyl-CoA will form my Krebs cycle. So let me just do this. In the Krebs cycle, somewhere at this point, I make an NADH. Go back and look at the Krebs cycle. At this point, somewhere here, I make another NADH. Somewhere here, I make an ATB. Somewhere here, I make an FADH2. Somewhere here, I make an NADH. The only thing left is caching them. Let's see. I'm going to show you where I came up with that from. I said here NADH, NADH, ATB, FADH2, NADH. That's from the Krebs cycle. That busy, crazy madness. Here, that's the one I'm referring to. So an NADH, the ATB, FADH2, NADH. All right. Since oxygen is present, I can cache. Nothing is preventing me from caching. So I need a new number for this because I never came up with a number with oxygen. What is the number? Add up. So I have this ATB. Sorry, let's start from the beginning. From here, the glycerol 3 phosphate right there. That's my start. Am I going to cache this one? I said, why not? Is this cytoplasmic or mitochondrial? That's cytoplasmic. We are on the cytoplasm. That's glycolysis. What kind of cell it is? Well, it's not a cardiocyte, and it's not a hepatocyte. Then it's going to be cached into 2. I said here, Where is it? Here. I said the cytoplasmic NADH will be cached into 2 if it's not a cardiocyte or hepatocyte. Okay, so let's continue. So this one will give me 2, 3, 4, 5, 6, 7 so far. 7 so far. Why 7? Because from this, that's mitochondrial. Every one of them will be cached into 3. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That's yes. And that's 2 ATP. This is just to show you. Of course, I will add billion variables to every question. As we will see, I gave you in the packet, in the Google Drive, many examples with the key, with the answers. You can't maybe answer every single one yet, but you should be able to answer maybe 95% of them, even with the conclusion of this video. So 2 and 19, look at the huge difference between using oxygen and not using oxygen. Don't forget that's cached into 2. So one more time, I said this one here is cytoplasmic. The cell is not a cardiocyte or hepatocyte, so will be cached into 2. So 2 here, that's cache money 3, 4. This will be cached into 3, so 7. This will be cached into 3, 10. This will be cached into 3, 13. This is cache money, 14. This will be cached into 2, 16. Then 3 more, 19. All right, I'm gonna stop at this point with this video, and I will send one more tomorrow. All right, everyone. Thank you for listening and watching.